Hello, this is Dr. Miller again, and this is walking you through how to do the pre-lab questions for lab activity 6.1. So this is a picture of the setup you will be using in laboratory. So we will have a source of an element, hydrogen, that we will energize with electricity. You can see that there's an electrical outlet here, so this hydrogen will emit light of certain wavelengths. As the electrons are bumped up to a higher orbital, and then as they fall back down, and they release energy in the form of light. And so we will be able to see that light. And so let's look at this setup. We have the hydrogen light here. We have a meter stick that's we're going to have, and we're going to measure how far the light goes away from the original source. We were going to be using a diffraction grating, and so this is what ours looks like. And if you move it around here, we can see, perhaps you can see that there's a source of light with our overhead light, and it's diffraction light. Maybe you can see there's some colors here. So this diffraction grating has 500 lines per millimeter. So that is one of the measurements we're going to consider. Oh, there you can see the diffraction of the light in the different colors. So when we look through our diffraction grating and look at the light, our light will be diffracted from the hydrogen source, and we'll see the lines at some area along the meter stick. We'll see it on both the right and on the left, and you'll indicate how far away that is. And so then also this diffraction grating is on this ring stand, and there's a pipette bulb here just to indicate where exactly this is in space. And so you're going to measure how far this is from the hydrogen light source. You're going to have an X on the tape that where it intersects between the different axes here, and so you will measure the distance that is. So let's look at some of the symbols we're going to use for the different measurements that are important. So your pre-lab activity refers to delta X. And let me use that in another pen. Delta X, and that is what they call the relative displacement of the different wavelengths of light. Oh, let's get that better focused. There we go. And that's also known as fringe spacing. So once again, that's the difference between the 50 centimeter mark and the marks on the meter stick. So that's the relative displacement. And you have a problem with that being given to you as in centimeters. So you need to pay attention to the units that is going to be given in. So another symbol that we're going to be using is capital D. And capital D is the distance between the grating and the light source. So that's capital D. And then there's a little d. When you know it, they make it a little bit complicated, but the little d is what's called the slit spacing. So we have on our diffraction grating, it says 500 lines per millimeter. So in order to find our slit spacing for our particular diffraction grating, we would have to take 1 millimeter and divide it by 500 to find our slit spacing, which is our little d. So big D will be a big number, and little d will be a little number, and this will be a relatively large number too. So now we need to think about some conversion factors that we're going to be using. So light is often given to us in wavelengths in the nanometer range, or it could be the angstrom range. So one of your problems has you look at it in the angstrom range. So 1 angstrom equals 10 to the negative 10 meters. 1 nanometer equals 10 to the negative 9 meters. Then you also could be using millimeters, so 1 millimeter equals 10 to the negative 6 meters. 1 centimeter equals 10 to the negative 2 meters. I'm sorry, this is 3. Why did I say 6? Negative 6. Because I skipped one. 1 micron or micrometer, and we use the Greek letter mu for that, equals 10 to the negative 6 meters. That's why I goofed up. So we have these different units. So we can either go through meters to convert one to the other, or we can take shortcuts. For instance, we could go 1 micrometer equals 10 to the 3rd nanometers. Because see, there's a difference between these two of a 3. So negative 6 to negative 9, nanometers being smaller than micrometers. Okay, so those are some conversion factors we will be using. So let's look at our problem. The first problem I want to do is the last problem, because I think it's the easiest one. So we will do number 4 on the back of your sheet first. So turn your sheet over, and we'll do number 4. So it says to look up the wavelengths of the emission spectrum for hydrogen in the CRC Handbook of Chemistry and Physics. The CRC contains emission data for all regions of the electromagnetic spectrum, but you need only emission data for the visible region, 400 to 700 nanometers. That's what our eye can detect. There is lots of electromagnetic spectrum, such as the X-ray, the infrared, that are outside what our eyes can detect, but our visible region is 400 to 700 nanometers. So that's what we're working with in lab. So the wavelengths in the CRC are given to you in angstroms, and we need to convert these data to nanometers and record the color and wavelength of each emission line in Table 6.1 on the data sheet. Show a sample calculation for the shortest emitted wavelength in the space provided. So here are the wavelengths from the CRC: 4,110 angstroms, 4,340 angstroms, 4,860 angstroms, and 6,560 angstroms. So we need to have a sample calculation for the shortest emitted wavelength in the space provided. So which one is the shortest? Well, this is in length and distance, so our 4,110 angstrom is the shortest. So we need to convert that to nanometers. So here's one way to do it. So we can go through meters. So we go back and look at the parameters I gave you, and we see that 1 angstrom is 10 to the negative 10th meters. So I want to get rid of my angstrom, so I put that on the bottom. 1 angstrom is 10 to the negative 10 meters. Now I look and I see, what is a nanometer? It's 10 to the negative 9 meters. So I want to get rid of my meters, so I put 1 meter here, and I put 10 to the negative 9 nanometers here. So these are what they equal. So these are conversion factors, and this is going to be used in dimensional analysis. So then I can cross through the angstroms, and I can cross through the meters. So when you take 4,100 times 10 to the negative 10 times, I'm sorry, this is a positive number, 10 to the positive 10, 9. So there's a lot of nanometers in 1 meter, so that's a positive 9. So 10 to the negative 9 times 10 to the positive 9, and we know what that number is, right? Because we're used to working with exponents. So 4100 times 10, if we multiply, we're actually adding the exponent, so a negative 10 plus a positive 9 gives us a negative 1. So that is the same thing as, well, in nanometers. So So we can express that as 410 nanometers. So that's the sample for the table 6.1 you're going to do on your lab report. So that's number 4. And I'm going to stop the recording right now and show you how to do the other 3 in another recording.